Today on Macaulay Math, we're finding derivatives. Finally. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, lesson number 6 on the definition of derivative. Our goals for today, we're going to use the limit definition to find a derivative. We're going to use the derivative to find the slope of a tangent line. And we're going to use the derivative to find a rate of change. The next section of calculus deals with the concept of the derivative. Derivatives have many practical applications, but the most basic use of the derivative is to find the slope of tangent lines to a function at any given point. Let's start with a demonstration. In this demonstration, we have a function f depicted here in yellow. And let's say that we want to find the slope of a tangent line of the function at x depicted here using the red dotted line. We recall that the equation for slope is given by m is equal to y2 minus y1 all over x2 minus x1. But in this case, we only have one blue point, and therefore we cannot calculate the slope of this tangent line because we need two known points. Suppose there is another value of x that is delta x units further to the right. The function value at x plus delta x is represented by the green dot. So the green secant line that passes through the blue dot and the green dot is an approximation for the slope of the red dotted line. Granted, it would be a bad approximation in this case, but we can make it a better approximation if we shrink delta x. If we let delta x get smaller, the green secant line becomes a better approximation of the red dotted tangent line. And if we let delta x shrink to 0, the green line becomes the red tangent line. The formal definition of derivative. The derivative of a function, f, at the point x is defined as, and this is some new notation for us, f with this a little apostrophe thing that we're going to call f prime. F prime of x is equal to the limit as delta x goes to 0 of f of the quantity x plus delta x minus f of x all over delta x. The slope of the tangent line at the value x is the value of the derivative at x. Now, this is one of the reasons that we made such a big deal out of the fact that a limit can exist even if the value of the function at the point does not exist at the beginning of our discussion on limits. It is because when we came to the formal definition of derivative, we knew that in almost every instance, this limit would not be able to be solved with a simple substitution. There are a number of different ways that you can denote the derivative of a function. I will regularly use all of these in an effort to help you get more comfortable with the notation. An important concept of differentiability, it does imply continuity. If a function has a derivative at a point x, then it is continuous at x. If a function is continuous at x, it may not be differentiable at x. There are points where a function is non-differentiable, and these usually look like sharp turns or vertical tangent lines. Example, using the function f of x equals 6 minus x squared. Let's have a quick Desmos demonstration of one of these points where we can see that a function is continuous but is not differentiable at a sharp turn. Let's say we want to define a function as f of x equals to absolute value x squared minus 1 absolute value. We can clearly see that 1, 0 is defined, and it looks as if it is continuous over that function. This is an example of a sharp turn. One of the cool features of Desmos is that I'm allowed to do the derivative and evaluate those. If I go f prime of 1, you will see that I get an undefined here. So the derivative of f at 1 is undefined. Why? Because I have this sharp turn. So that's an example of a place where it is continuous, the derivative does not exist. An example, Using the function f of x equal to 6 minus x squared. Part A, use the limit definition to find the derivative of f. And part B, find the slope of the tangent line at the point 1,5. So let's start with part A. And we remember from the previous page that f prime of x will be equal to the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. All right, so we're going to plug in. Let's start with the limit. I have not yet evaluated the limit, so I have to write the limit, and we'll let that delta x go to 0. The first thing we're going to write here is f of x plus delta x, so I'm going to plug this x plus delta x in for x into this expression here. So I'm going to have 6 minus the quantity x plus delta x squared minus this f of x, and f of x is 6 minus x squared, so we'll write that 6 minus x squared, and I'm subtracting away that whole quantity, so I'm going to put parentheses around it for now, and then I'm eventually going to distribute this negative. That's going to stay all over delta x. Okay, so now I have to square this binomial, and remember, when you're squaring a binomial, you have to multiply x plus delta x times itself and distribute. So we still have to write this limit, so the limit as delta x goes to 0 of 6 minus the quantity x squared plus 2x times the quantity delta x plus the quantity delta x squared. And then let's just distribute this negative. So I have minus 6, and then minus a negative becomes plus a positive x squared. And that will all be over delta x. All right, so let's distribute this negative to each term. The limit as delta x goes to 0 of 6 minus x squared minus 2x times the quantity delta x minus delta x squared minus 6 plus x squared all over delta x. Now I see that I can cancel out this 6 and this negative 6, this negative x squared and this positive x squared. I have only left the limit as delta x goes to 0 of negative 2x delta x minus delta x squared all over delta x. Now the good news is I've got 1, 2, 3 terms. All of them have a factor of delta x, so we can cancel out. And so I have the limit as delta x goes to 0. Negative 2x delta x cancels, leaving me with just negative 2x. Negative delta x squared divided by delta x is just negative delta x. And then delta x divided by delta x is 1, but we wouldn't put 1 on the bottom. This thing we can evaluate. If delta x goes to 0, it is not undefined. If delta x goes to 0 anywhere above here, so we can evaluate this. And now, since I am evaluating it, letting delta x go to 0, I have negative 2x, that's it. And then delta x goes to 0, and since it's 0, we wouldn't write it. And this is our final answer. So f prime of x is going to equal negative 2x, and we'll put a box around that, and we'll say we're done with part A. Part B says find the slope of the tangent line at the point 1,5. All right. So the slope of the tangent line, part B, to find that slope of the tangent line, what we're going to do is we're going to take our derivative and we're going to plug in that 1 value there. So in this case, negative 2 times 1 would give me negative 2 is the slope of our tangent line at 1,5. Now, just as a real quick check, let's go back over to Desmos and let's type in y equals negative 6x squared. Let's zoom back out. 1,5 is clearly a point on our graph. All right, and if I were to draw in a tangent line, it looks as if the slope of that tangent line is going to be negative and fairly steep. It does make sense that our slope will probably be -2, which we came up with right there. The next example. Use the limit process to find the derivative of this expression right here. Here's what we'll do. We'll start by writing the limit process. So we'll say f prime of x, and I'm just going to plug in the definition, and you can check back to see what the definition is. The limit as delta x goes to 0 of 3 over the square root of x plus delta x minus 3 over square root x all over delta x. Now, if I let delta x go to 0 here, I would have a division by 0. So I have to do something. We're going to subtract fractions. And to do that, I need common denominators. All right, so again, have not evaluated my limit, so I need to write it. And to get a common denominator, there are no common factors here, so I have to multiply by a funky 1. And so it'll be the square root of x over the square root of x times the quantity 3 over the square root of x plus delta x minus 3 over square root of x times the square root of x plus delta x all over the square root of x plus delta x all over delta x. Now, here we're going to do a little distributing. And we'll get the limit as delta x goes to 0 of 3 delta x over, now I'm just going to leave it as the square root of x times the square root of x plus delta x minus 3 times the square root of x plus delta x, and that's going to be all over delta x. All right, so a little bit better news. When I let delta x go to 0 in the numerator of this fraction, I won't get a division by 0, but I still will here. So we're going to try and rationalize the numerator. And again, we're going to multiply by another funky 1. It's going to get kind of big. So the limit as delta x goes to 0 of 3 square root of x minus 3 over x plus delta x all over the square root of x times the square root of x plus delta x. And then we're going to put all of that over delta x, and we're going to multiply by a funky 1. And that funky 1 is going to be the conjugate of this. And so the conjugate will have 3 square root of x, and then it'll be plus this time 3 over x plus delta x all over, and since we're multiplying by a funky 1, it has to be 3 square root of x plus 3 over x plus delta x. I'm going to ask you to recall that a plus b times a minus b is equal to a squared minus b squared. So in this case, let's extend the page. Limit as delta x goes to 0, 3 square root of x will be my a. So I want to square this. That will give me 3 squared is 9. Square root of x squared is just x. And then it will be minus, I'll get my 3 squared, that's going to be 9. And then the square root of x plus delta x squared will just be x plus delta x. And that'll be all over. Now, this expression times this expression is going to be really ugly at this point. But when I let delta x go to 0, a lot of stuff is going to cancel out, and it's actually going to be pretty nice. So we're just going to write it out for right now and leave it as a placeholder. And sometimes it's just better to do that. I need a parenthesis here. And so what's going to happen is when I distribute this negative 9 to these two terms, the limit as delta x goes to 0, I'll have 9x minus 9x minus 9 delta x all over, and I know this expression is ugly, but we'll rewrite it, x, or square root of x, times x plus delta x times the quantity 3 square root of x plus 3 square root of x plus delta x all over delta x. Now, here's where it gets a little bit better. I know it's ugly looking right now, but this x, this 9x there cancels with this 9x. This delta x here cancels with this delta x there. And so here's what I'm left with. I am left with the limit as delta x goes to 0 of just negative 9 on top all over the square root of x times the square root of x plus delta x times the quantity 3 square root of x plus 3 square root of x plus delta x. We'll extend that bottom line. I'll put a parenthesis there so that we know that it's a multiplication. And just to be on the safe side, we'll put a parenthesis back up there to remind us. Now here, it's still ugly, and I get that. But here's the whole purpose. In the step above, if I let delta x go to 0, I have this delta x on the bottom, and I have a division by 0. Can't do it. But if I let delta x go to 0 here and here, I still have this x, and I still have that x. So it doesn't give me a division by 0. So the whole purpose of this exercise was trying to figure out a way to rewrite this expression in a way that when you let delta x go to 0, you don't get an undefined. And we don't. So now I'm doing the limit. So I have my negative 9 on the top. I have my square root of x. This delta x has become 0, so I have another square root of x. And then it's a multiplication. I have my 3 square root of x. And then again, because I let this delta x go to 0, it doesn't make this expression 0. It makes it square root of x. So I have plus 3 square root of x. Have my parenthesis. Do a little simplification here. And these two are like terms, so I can combine them. So I have negative 9 over square root of x times square root of x is just going to be x. And then 3 square root of x plus 3 square root of x is going to be 6 square root of x. All right. Well, 9 and negative 6 have a factor of 3. So if I divide a 3 out of both of those, I'll get a negative 3 on the top, and I'll get a positive 2 on the bottom. So it's just proper to write this 2 there, and then I have x square root of x. And then we've done a lot of work. We should probably put the square root up on top, and that isn't going to be too bad. We could get away with that fairly easy and go 3 square root of x over 2x squared, and we'll call that our final answer. All right, that one was a lot of work. All right. Example, in the graph to the right, the function f is defined by the blue curve. Use the graph to draw an approximation of f prime. All right. So I want to look at this, and I have some features. All right, so f prime. What is f prime going to look like in this function? Well, f prime finds slopes of tangent lines. So if I think about it, let's just, as a for instance, and I pick this point right here, and I draw the tangent line. That slope of that tangent line is going to be positive, and it's going to be pretty big. Okay? So it'll be positive and be pretty big. But if I draw a tangent line, let's say right here, it's also, the slope of this tangent line will be positive, but not as big as the slope of the tangent line over here. And if I pick this point right here at x equals to 0, the slope of that tangent line, the slope of this tangent line is probably close to 0. If I pick a point here and I draw this tangent line, the slope of this tangent line is negative and large, but not as large as the slope of this tangent line. It's negative and also large. So as I draw my slopes, they should be very big and positive, and then they should get smaller and smaller and smaller until I get to 0 right here. And then they're going to decrease and become negative and get larger negatively as I go from here to here. So the easiest way to draw in a line is we're just going to say that something like this might be a decent approximation of f prime. Why? Because at this point, let's say it corresponds to that point, I have a value that's positive and large, and it gets smaller and smaller and smaller until I get to x equals 0, when the slope of the tangent line is 0, and the value of this f prime is 0. And then once I get past x equals 0, the function tends to decrease, so the slopes of the tangent lines are all going to be negative, so the values of the derivative will be negative, and this thing gets smaller and smaller and smaller, or larger negatively if that makes more sense to you, as we move further and further along the x-axis. So this is going to be my approximation for f prime. Is it the only one? Probably not, but it's a good one for our discussion here. Final example, use the following. With respect to the limit definition of derivative, find what we're going to call f and the value for which f prime is being evaluated at c. Okay, it looks to me like they've plugged in some value for c. So what they're asking for is to find out what that f is. So we remember that f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over square root delta, or all over delta x. And so what they're saying is that they've plugged in some value c. All right. And so we're trying to come up with a function, and it looks like they've evaluated this function. All right. So if I did it this way, let's say x is equal to c, I want to figure out what that c is going to be. So let's plug in our x equal to c and rewrite that limit definition. So I got the limit as delta x goes to 0 of f of c plus delta x, and then minus f of c all over delta x. All right, so I look at this. I've got a third to the third power here, and then I've got f of c. All right, well, if I got a third power, so clearly my f of x is going to have something to the third power. All right, and so what to the third power is 8? Well, 2 to the third power is 8, and if it's minus, so if I go 2 to the third, but I'm subtracting, I have a minus there. But if I go negative 2 to the third, and then go minus, negative 2 to the third would be negative 8, and then negative 8 would be positive 8. So I'm guessing that f of x is x to the third, and then I'm going to let c equal to negative 2. And then negative 2 to the third would be negative 8, and then I subtract it. And then this negative 2 helps me to confirm that. So I feel fairly confident that that is going to be right. If I let f of x equal x to the third and c equal to negative 2, and I plug back into this equation, I'll get the limit as delta x goes to 0. I will get c is negative 2 plus delta x, and that has to be to the third, minus negative 2 to the third all over delta x. Well, hey, that looks like that's going to work because I have the limit as delta x goes to 0 of negative 2 plus delta x to the third, and then it'll be plus 8 all over delta x, which is what I have here. So I feel very confident with that answer, if I put a B there. All right, folks, that's all I got. So The Star Wars fun fact of the day: in Episode 1, The Phantom Menace, Qui-Gon Jinn's communicator was modeled by using a resin cast of Gillette Sensor XL ladies razor handle as a base. And you can see the little curved bit with the little squiggly lines right there. They just added some little bits on top and these little tchotchkes on there. So not everything is made from scratch. That's all I got for today, folks. Have a good day. Goodbye.